Now, let's add some restrictions to bring our example closer to real-world conditions. Consider the same sender and receiver nodes, the same network, but this time, assume the router with the shared output link has a finite buffer. This will change everything, as now, when the link reaches its capacity, more and more packets will be queued. And after the link buffer reaches its capacity, we will start to experience packet drop. Those lost packets will need retransmissions. Therefore, the transport layer rate of transmission will include those retransmitted packets in addition to the data from the layer above. Note that this increased transmission rate at the sender side will not result in an increase in the lambda out at the receiver side. Let's add another simplifying assumption to this analysis. Let's assume the senders have perfect knowledge about the router buffer state. Therefore, they can send data only when the router has buffer available. In this scenario, the knowledge about the router buffer will prevent losses at the router. Therefore, the lambda prime n will stay the same as lambda n, and we will maintain the same throughput as in the first scenario. One step closer to reality. In this step, assume sender does not have information about the availability of the buffer in the router. Therefore, loss can happen. However, assume that the sender will know for sure when a packet is lost and will only retransmit in that situation. With this assumption, we no longer have equal values of lambda n and lambda prime n as we reach the shared link capacity. Therefore, as the sending rate reaches half of the shared link capacity, we will see loss, and therefore retransmissions. And that means sender transmits more data than received at the destination. The more retransmissions will be needed with the increase in the transmission rate from that point on. This will cause wasted capacity due to retransmissions required to compensate for the lost packets. Another step closer to reality. Let's assume we may also have premature timeouts. That means packets that are considered lost might have actually been delivered at the receiver side. This will cause another set of costs to our network that now has to transmit packets that were originally delivered properly to the destination, but due to wrong detection of loss at the sender, were retransmitted and are received in duplicate copies at the receiver side. So, by sending rate getting closer to half of the link capacity, even more retransmit packets are being sent. This means congestion in the network has caused even more work. This more work is in terms of retransmissions that are involved in reaching the same throughput observed by the application, which we call good put.